Okay, so in the last lecture, we were kind of doing the counting of degrees of freedom uh, in the uh, class of quantities that one could write down by looking at metric and its derivatives and so on, versus the amount of freedom that one have when one does coordinate transformation. And we showed that the coordinate transformation has sufficient freedom to locally set the metric to Minkowski form, and also has additional freedom to kind of do transformation which would preserve the local Minkowski metric. The derivative of the transformation, or rather second derivative of the transformation, had the property that it could set all components of first derivative of the metric to 0. Okay, so it has sufficient number of freedom to arrange those values to whatever it wants. Okay, in particular, they can be set to 0 also. When we looked at the third derivative of the coordinate transformation, which was related to the second derivative of the metric, in that case, we found that the second derivative of the metric had 100 independent parameters, whereas the third derivative of the coordinate transformation had only 80. So that left us with about 20 parameters which no coordinate transformation could fix. And we wanted to, we are asked the question as to how do we characterize these 20 components. And one of the things that we did in the previous class was to look at the Riemann tensor, and we kind of defined the covariant form of the Riemann tensor by pulling the contravariant index down. And we showed that this Riemann tensor has following properties. That, of course, this form is written in a frame in which gamma is 0, but the derivative of gamma is not 0. But what we found was that the Riemann tensor is antisymmetric in first two indices, namely alpha beta here, and antisymmetric in last two indices, gamma delta. And in addition, we also found that it has one more symmetry, which is if you pairwise exchange alpha beta and gamma delta, then the Riemann tensor is symmetric. So these two are antisymmetry relations, whereas this is a symmetry relation. Okay, so that is the symmetry that we found, and we wanted to check what is the total number of independent components that the Riemann tensor could have. Okay. Of course, in addition to this, there is one more identity that the Riemann tensor satisfies, which is what is called the algebraic Bianchi identity, and that is written out here: R alpha beta gamma delta plus R alpha gamma delta beta plus R alpha delta beta gamma equals 0. This is basically just holding alpha fixed and doing a cyclic permutation of beta gamma and delta. Okay, and if you do that, then the Riemann tensor vanishes. This sum of these three components of Riemann tensor vanishes. It turns out that although it looks like it's a four indexed object, in reality this is just single condition, because anytime any of these indices, any two of these indices become identical, this identity is trivial. Okay, by trivial one means that we know a corresponding expression already. Okay, so therefore only place where this identity is non-trivial is when alpha is not equal to beta, which is not equal to gamma, which is not equal to delta. And this is true of all pairwise relations. Alpha is not equal to any of the other variables and so on. Okay. And since we are in 4 dimensions, this equation therefore imposes only single condition. Okay. So, because all alpha, beta, gamma, delta take 4 values. Okay. And therefore it is also obvious that if alpha, beta, gamma, delta had taken say 5 values, then this is not a single condition. Okay. Because you have to choose 4 out of those 5 indices, and therefore it would actually reduce, it would actually become 5 equations. Okay. But that is of course in 5 dimensions. Okay, fine. But since we are going to exclusively work in 4 space-time dimensions, this is a single identity, and therefore the total number of components that we have for Riemann tensor subject to these conditions, uh, uh, that number is reduced by one more because of this condition. Okay, And of course, the exercise that we are doing here is basically to check that that number of degrees of freedom plus this single condition should give you total number of independent components to be 20, and those are the ones which the coordinate transformation cannot fix. Okay, and we have given a tensorial description of it. So if they are non-zero, then uh, in one particular frame, then they will be non-zero in all other frames. Okay, now of course, that there are 20 independent component of Riemann tensor does not necessarily mean that all 20 components need to be non-zero all the time. For example, if you take Minkowski metric, then all components are zero. Okay, and therefore uh, it doesn't matter which 20 of these you choose, because all 100 all components of Riemann tensor are essentially zero. Okay, they are not 100, really 20 only. Okay, fine. So after that, what we did was that we uh, looked at the additional condition that the Riemann tensor satisfies, and that is what's called the differential Bianchi identity. And that equation is written in this form. This uh, square bracket enclosing these things implies that you do cyclic permutations of these and write down the equation, and that's how is this equation. Okay, so beta gamma alpha, gamma alpha beta. That is this notation. Okay, so if you look at this condition, then this is a differential Bianchi identity, and since it involves taking derivatives, it actually does not uh, reduce the number of components, unlike the algebraic equations do. Okay, and what we did last time was actually checked that this Bianchi identity, we actually showed that this Bianchi identity is true. Since this Bianchi identity involves covariant derivative of a tensor, and therefore this is a tensorial equation, all these quantities are tensors. Okay, if you can show that this identity is true in one particular frame, it is true in all other frames. So we chose a convenient frame to do the computation, a frame in which the Riemann crystal connection is zero. That reduces this covariant derivative to ordinary partial derivative, and we explicitly computed these three derivatives and just added them. Okay, and when we add these pieces, we find that this expression is explicitly zero in the coordinate system in which Riemann crystal connection vanishes. And since it's a tensorial equation, if it is zero in one coordinate system, it is zero in all coordinate system. Okay, in fact, this identity is related to the so-called Jacobi identity satisfied by the covariant derivatives, and that relation, to get that relation, let's kind of look at how the covariant derivative acts on a say contravariant vector. Okay, so this relation is given by this, the d alpha on v beta. Remember, when you have a contravariant index, if the covariant derivative is acting on that, then you have a plus sign here. If you have a covariant index, then you have a minus sign. That is how the covariant derivative acts. So this is how the action of the covariant derivative is defined on a contravariant vector. Okay, once you take that, then yeah, yeah. So once you do that, then you could ask what is the commutator of two covariant derivatives, and we kind of computed this also last time, that you explicitly compute this. You get minus signs here simply because that is the time when the covariant derivative is acting on a covariant index object, and you can write down this expression. Okay, what we did was we explicitly expanded the quantities, all these pieces, and we found that uh, uh, whenever there is a derivative acting on the vector v alpha or v delta or whatever, okay, those terms explicitly cancel. The time the terms which do not involve derivatives acting on v, okay, those are the terms which survive, and those terms basically give you the Riemann tensor. So what we learn is that commutator of two covariant derivatives gives you the Riemann tensor. Okay. Now this is something we had already seen in electrodynamics, that commutator of two covariant derivatives actually gives you field strength. Okay. Which is also in the in a little more mathematical language, it's called curvature. Okay. So f mean is also called curvature of the corresponding gauge field, or in mathematical language would be called corresponding gauge connection. So a mu is gauge connection and f mu is the curvature of that connection. Similarly here, gamma is the connection and r is the curvature of that connection. Okay. And therefore, exactly the way we found in the electrodynamics, that the commutator of two covariant derivatives gives you the field strength or curvature f mu. Like that, here also we find commutator of two covariant derivatives gives you Riemann tensor. Okay, fine. So, so once you do this, this is something we have done explicitly. Now, what you could do is you can check this explicitly by computing this expression, and if you set this uh, kind of sum of these double commutators equals 0, which is what the Bianchi identity is, okay, you would automatically recover the differential Bianchi identity. Okay, this equation. Okay, it's not very difficult to guess how you would get it, because um, in the double commutator, if you look at the inner commutator, that already is related to Riemann tensor. So what you need to really do is to take this equation and act it on a contravariant vector. Okay, and just follow the stuff that we have done. Okay, and check what you get. Okay, you should be able to recover the differential Bianchi identity. Okay, so so is this okay? Is some kind of a recap of what we did last time, but any questions about that? Okay, if not, then let's go ahead and uh, let's write down two more tensors which we can construct out of this Riemann tensor. And to do that, let's go back to the original form of the Riemann tensor, which has one contravariant index and three covariant indices. And from that, we can construct what is called a Ricci tensor, which is R alpha beta, which is basically Riemann tensor with the one of the contravariant index contracted with the one of the covariant index in precisely this fashion. Okay, you contract the so if you list them as contravariant indexes first and covariant indexes are second, third, and fourth, then the first index contracts with the third index. Okay, that is the contraction. Okay, in case you contract first index with the say fourth index, okay, then remember last two indices are antisymmetric in the Riemann tensor case, and therefore if you contract the contravariant index with the last covariant index, you would get a Ricci tensor with a minus sign. Okay, simply because there is a sign between them. So this is clearly a fixed convention of defining Ricci tensor by contracting the first the contravariant index with the second covariant index. Okay, fine. Uh, so this definition is kind of unique. You doesn't matter which book you look at. Okay. The next tensor that we define is rank. This is of course a rank 2 tensor, and you can check actually that this is symmetric tensor. Okay, that means R alpha beta is same as R beta alpha. Okay, so this of course uh, is not immediately obvious from the Riemann tensor form, because we haven't said anything about the symmetry properties, but if of this object, but we have definitely talked about the symmetry properties of all covariant index Riemann tensor. But nevertheless, if you write down this expression explicitly, you can always check that the Ricci tensor is symmetric in alpha and beta. Okay. Now, the fact that Ricci tensor is symmetric in alpha and beta, you can of course take a trace of it. That means you can choose the indices to be alpha alpha. That can be done by contracting that with the inverse metric. And if you do that, then you get a tensor with no index. That means rank 0 tensor, which is what we call a Ricci scalar. Okay, so these are two tensors that you can construct from Riemann tensor, and clearly Riemann tensor carries all the information, but not all of that information actually translates into information of that Ricci tensor carries or a Ricci scalar carries. Okay, so uh, and that you can check. I mean, the total number of independent components of Riemann tensor versus total number of independent component of Ricci tensor, these numbers would differ. Okay. Fine. So let's kind of go back to the differential Bianchi identity and do a double contraction of it. By double contraction, I mean you multiply that by two inverse metric components. Okay, so we have this d alpha r beta gamma delta sigma, d beta r gamma alpha delta sigma, d gamma r alpha beta delta sigma, where delta sigmas are just spectator indices and alpha beta gamma are cyclically permuted. We contract the index alpha with delta and beta with sigma. Okay, that is what we want to do. Okay, so if you do that, then you get an expression where remember that the metric can be used for raising and lowering indices. Okay, which is what we did here also, that we just uh, use g alpha beta to raise one of the index, and then the index which has been raised has the same in I mean, it's the same index as the index which is downstairs, because if you raise beta using g alpha beta, then the upstairs index is alpha, so you get r alpha alpha, which is of course a trace, and therefore it's a scalar quantity and doesn't transform under general coordinate transformation. Okay, so we will use the same thing here. The inverse metric will basically raise indices, and you get quantities which is like d upstairs alpha r with beta gamma alpha beta, plus here we would be raising the index delta up. Okay, uh, oh, I forgot to write one index. There's a alpha and alpha here, so it is double contracted. That's bad. Okay, so r gamma alpha alpha beta, that's how it should be. Okay, uh, sorry for that. The same plus d gamma uh, alpha beta alpha beta. Okay, so I have chosen to write it in this fashion, but it doesn't matter if you had written it using these quantities. These alpha betas would have been upstairs and these would have been downstairs, but that doesn't really matter. Okay, but notice one thing, that if you look at this Riemann tensor, then something which I told you a few minutes ago, that if you contract the contravariant index with the last fellow, then it would give you a negative of the Ricci tensor. Okay, because the Ricci tensor is defined in this fashion. So instead of gamma being the second fellow, had it been the third fellow, then you would actually get a negative sign. Okay, and that is what will happen here. We will rewrite these quantities in terms of uh, the Ricci tensor and Ricci scalar, and we get the expression like this. This would be the negative of the Ricci tensor. Okay, I have swapped these indices alpha and gamma simply because it is symmetric in alpha and gamma. Okay, this uh, modulo this typo, the alpha index is contracted. So this is a Ricci scalar r gamma beta, which is same as r beta gamma, and the last fellow is double traced Riemann tensor, which is of course a quantity which does not carry any space-time index, and therefore it's a Ricci scalar. Okay, so we land up with this equation. If you collect these pieces together, you will find that up to a sign and a factors put of two kind of pulled out, you write down this expression as d alpha of r alpha gamma minus 1 by 2 d gamma of r is equal to 0. Okay, so this is the equation which is the same equation that, I mean, this is the equation which is derived from the differential Bianchi identity. Okay, Fine. Is there any question? Okay, maybe I hope I'm connected. This thing. So yeah. So what we'll do is we'll use this equation to define new tensors. Okay, and so let's define what is called the Einstein tensor, and the, so we'll write the Einstein tensor as capital G alpha beta with covariant indices, and we write that as R alpha beta minus half times G alpha beta R. Okay. Uh, so this is just a definition of the Einstein tensor. But if you take a covariant derivative of Einstein tensor, if you contract the indices in this particular fashion, then you will find that d alpha of g alpha beta is equal to 0, which directly follows from this differential Bianchi identity that we have derived. Okay. So, so from this expression, you can kind of use the fact that you can write down Einstein tensor and replace this equation by the covariant derivative contracted with Einstein tensor, giving you 0. Okay, fine. So this equation is of course going to be useful when one tries to kind of study general relativity further, uh, particularly how it reflects onto the matter coupled to gravity and kind of situations. Okay, fine. So let's define one more tensor, and that is called the Weil tensor. And typically, it is kind of the easiest way to define it is when it has all covariant indices. Although it has interesting properties when it has at least one not at least, when it has one contravariant index. Okay, we'll come to that in a moment. But this is an easy way of defining the fellow. C alpha beta gamma delta is R alpha beta gamma delta, which is the covariant form of the Riemann tensor, minus half times G alpha gamma times this Ricci tensor R beta delta minus G alpha delta R beta gamma, which is again a Ricci tensor, minus G beta gamma R alpha delta plus G beta delta R alpha gamma plus 1/6 of Ricci scalar times this particular combination of metric components G alpha gamma G beta delta minus G alpha delta G beta gamma. Okay. So Weil tensor in particular has the property that it has exactly same symmetry properties that the Riemann tensor has. Now, of course, this component of the Weil tensor has Riemann tensor properties, but all other pieces which are contributing uh, to the Weil tensor also have the same property. Namely, it is antisymmetric in alpha beta, it is antisymmetric in gamma delta, but if you do a pairwise exchange between alpha beta pair and gamma delta pair, then C alpha beta gamma delta is equal to C gamma delta alpha beta. Okay. Fine. So in addition, Weil tensor has a property that it is traceless. Okay. So by traceless, I mean that if you choose any two indices of Weil tensor and contract them, the Weil tensor vanishes. Okay. So now this property, of course, is not there for the Riemann tensor. Because if that was the property, then we wouldn't get Ricci tensor or Ricci scalar, because we do contract indices so that we go from 4 indexed object to 2 indexed object, and then further down to an object which has no indices, namely Ricci scalar. Okay. So, but these quantities are arranged in such a way that if you try to take a trace, contract two indices, Okay, then you can show that various terms would conspire to get the answer 0. Okay, now of course, given the fact that C alpha beta gamma delta is antisymmetric in alpha beta, you cannot contract this pair, and similarly you cannot contract gamma delta pair, simply because contraction is done by G alpha beta by metric, and metric is symmetric in those indices. So product of symmetric and antisymmetric uh, uh, tensors or matrices, for example, would just be 0. Okay, so therefore only possible contraction would be one index from first pair with any index from the second pair. Okay, so that still leaves you with sufficient number of contractions. Okay, fine. So as I was saying, that while tensor has exactly same symmetry property as the Riemann tensor, and that I have kind of uh, quickly listed like this, that it is antisymmetric in alpha and beta, that's the statement of the square bracket, and antisymmetric in gamma delta, so that's the same square bracket. And if you change pairwise, okay, then it is symmetric. Oh, wait a minute. This statement actually is a statement that you are doing a pairwise exchange here, and therefore it doesn't flip sign. Okay, but if I do only one flip, then I should have written a minus sign there. Okay, so we are writing down the antisymmetry property of both the pairs here. Okay, and the last property is, of course, the algebraic Bianchi identity, where you fix one index and cyclically permute the remaining three. Okay, fine. So besides the fact that while tensor is traceless, it is also called a conformal tensor. Okay, and so we will see in a moment why it is called a conformal tensor. Uh, but it is called a conformal tensor when it is written in this particular form. Okay, namely, it has one contravariant index and three covariant index in three covariant indices. Okay, so so let's check that. Okay, but before we check that, let me just explain what one means by uh, conformal transformation. By conformal transformation, I mean that you write down a metric which is under coordinate transformation undergoes a local rescaling. Okay, so that means you have some G alpha beta which goes to a new G prime alpha prime beta prime, which can be written as some overall scale factor. I, we can call it, say, omega of x times G alpha beta of x. Okay, that is the kind of stuff. Okay, now of course, besides just having overall factor, you could also have other pieces which would be part of the ordinary general coordinate transformation, which is del x by del x prime kind of pieces. But uh, the local rescaling is a statement that there is a overall factor which is a function of local coordinates, which is sitting outside the coordinate transformation that you are doing. Okay, so this is what I meant. Okay, so now, of course, as I said, that you could have had some del x by del x prime kind of whole squared kind of piece sitting around there, but I'm not looking at that right now, just to kind of save contamination by those terms in writing down these expressions. Okay, but if you write those pieces and keep track of each piece of every piece carefully, it will give you a result which is no different from what we will derive right now. Okay. Right. So what we want to do is basically do this transformation right now. Okay. So we don't change coordinate system. Only thing that we do is to write down a new metric, which is a scaled version of this original metric. And the scaling that you do depends on the space-time point. Okay. So at one space-time point, you scale it by, say, a factor of 2, and some other space-time point, you could scale it up by, say, factor of 5. Uh, it's all fine. Okay, it's all allowed because you're doing local rescalings. Okay, as against the global rescaling where one metric to another metric scaling is just fixed factor. Okay, that factor could be some 5. Okay, then everybody is scaled by 5. Okay, we are looking at local one. Fine. So as usual, we'll resort to frame in which we can kind of simplify the formulae for a Riemann tensor so that we can do this computation with the least number of possible components of or terms that can be used to describe the Riemann tensor, and then appeal to the tensorial property of the Riemann tensor and say that like whatever we have done in this frame is applicable to all other frames. Okay, and of course the most convenient frame is the one in which the derivative of g vanishes. Okay, which is same as gamma vanishing. Okay, we have already computed the Riemann tensor in this frame and it takes this form. And what we'll do is we'll kind of use this form of the metric as of the Riemann tensor and replace the metric by the locally rescaled metric. Now notice that that's a non-trivial thing to do simply because omega is a function of x, and Riemann tensor written in this particular form involves derivative acting on metric. So of course by chain rule there are terms involving derivative acting on omega. Okay, so we'll keep track of each of those pieces. Okay, fine. So so if you write this in the G tilde frame, then yeah, okay, I should write in a G tilde here. Okay, uh, d beta d del beta del delta of G tilde alpha gamma. Okay, and that quantity would be uh, something like this, where G tilde is omega times G, and when you take the partial derivative in, it may go across omega and act on G, or it would act on G and not act on, or it would act on omega and not act on G. Okay, it's just a simple chain rule. Okay, so you can do this and you can write down this final expression. Okay, what we have done here is that when you take a del beta through, then if when you take the del beta through, then it could have acted on omega. Okay, or it could just pass through omega and act on derivative of G. Okay, what we have done is we have kept only the second term, that is passes through omega and acts on derivative of G. And that is because if beta acts on omega, then that quantity is multiplied by single derivative of G. But we are already working in a frame in which single derivative of G vanishes. Okay, so as a result, out of the two terms that you would get here, one of the term is zero because of the choice of the frame. Okay, so therefore we land up with only this term here, and same here in this case, that del beta now has to act on del delta of omega, because if it just goes across and acts on G, then that term would involve derivative of omega multiplied by derivative of G. But derivative of G again vanishes because we are working in that choice of frame. Okay, so therefore this expression becomes simple. Either both derivative act on G or both derivative act on omega. Okay, fine. So what we need to do is to take these pieces and plug them back into this. Okay, so you write down R tilde is equal to all these derivative acting on G tilde everywhere, and then you write down G tilde as omega times G, plug it in, and that is the computation that we have done here, modulo the typo on the left hand side, that should have been G tilde. But once you do that, then you realize that a double derivative can be written as two terms, either double derivative acting on G or on omega. Plug it into this expression. Okay, so here's a small exercise. If you do that, then you get R tilde is equal to omega times R plus half times second derivative acting on omega times G plus second derivative acting on omega times another component of G, and so on. Okay, you get four terms like that. Okay, now it's not very difficult to find, kind of guess that the first term would be like this, simply because when you look at this expression and plug it back into the Riemann tensor form, okay, then there exists the first term on the right hand side, okay, is omega times the same kind of piece, but instead of G tilde, which is what this should have been, you get a G. So if you had an equation with a G tilde everywhere, there is this one class of terms which are like omega times the same class of derivatives acting on g, and similarly here and in the other two terms also. So you can just pull omega out, and whatever you get is actually a Riemann tensor with respect to metric g. Okay, so this piece is kind of trivial. The other piece is just you have to carefully collect terms with, I mean, not too much care is required, but like, collect these terms and write them down. The factor of half is already in the definition of the Riemann tensor. Okay, it's a reasonably straightforward piece. Okay, good. So this is an exercise, but if we agree, yeah, sorry, a small typo here. I should have put a minus sign in the last piece here, but I'll do that. I'll correct it. Too many typos. Okay, but once we agree that we get the Riemann tensor written for the rescaled metric in this particular form, okay, then we just use that and plug it uh, into the wild tensor form. Okay, now once you have done this computation, then doing the same computation for Ricci tensor is not difficult. All you have to do is to contract indices. Okay, now only thing that you need to be careful is the following: that when you want to contract indices, you will contract alpha with gamma, and that will be done by multiplying by inverse metric. Okay, the inverse metric on the left hand side that you'd use would be G tilde alpha gamma with alpha gamma contravariant indices. Okay, but that's not the metric that you will use on the right hand side. Well, you will use the same because you will multiply by the same function on both sides, but you would want to use G alpha gamma to contact this alpha gamma indices of the Riemann tensor. Okay, but G alpha gamma is related to G tilde alpha uh, gamma through this relation. There is a factor of omega sitting around between them. Okay, now omega is sitting between these for contravariant, for covariant indices. For contravariant indices, there is a omega inverse sitting around. Okay, so that is one thing you need to be careful with. But once you do that, then you should find that the r tilde beta delta should be equal to r tilde beta delta r beta delta plus half times this quantity. Okay, you can do the same exercise with the Ricci scalar, and you can show that r tilde is equal to omega inverse times r plus 3 times omega to the minus 2 Laplacian, local Laplacian acting on omega. Okay, so it's a straightforward check. Once you convince yourself that this is right with the minus sign here, then you can derive these results. Okay, so, so but once you do that, now then we can use all these relations in the uh, wild tensor expression and check how the wild tensor transforms. Okay, but before we do that, I just want you to remember a specific mnemonic which would be useful for you to kind of make useful for you to understand how to uh, count how many factors of omega you would actually get. Okay, now to do that, maybe should split the screen. Okay, maybe I can raise it a little. Okay, so I have a better expression somewhere else downstairs, but anyway, since I have found one. Okay, so first thing that you notice is that when you write down a Riemann tensor with all covariant indices, okay, it involves only metric with covariant indices. and that is it, nothing more. Okay, so therefore, if you if you do a local rescaling of the metric, then the Riemann tensor to Riemann tensor relation has to have a factor of omega there, because imagine that you replace this g by say omega times some g prime. Okay, then these derivatives will of course act on omega. Okay, but when they do not act on omega, then the omega just pulls out of the entire expression. Whenever omega pulls out of the entire expression, you should again recover a Riemann tensor, which is what is the first term here. Okay, and because this expression is involves only covariant form of the metric, if covariant form of the metric goes to omega times another covariant form of the metric, then Riemann tensor would just go to omega times Riemann tensor plus an additional piece, of course. But this power is easy to remember because Riemann tensor with all covariant indices is proportional to metric with covariant indices. Okay, but contrast that with what happens with the Ricci tensor. Okay, so let's go down a little here. Okay, so to get a Ricci tensor, you have to have one index upstairs for the Riemann tensor. Okay, to get one index upstairs, you have to multiply the covariant Riemann tensor by G inverse. Okay, with the metric with two contravariant indices. Okay, if you do that, then the contravariant index metric transform as omega inverse. Okay, and therefore Riemann tensor itself, covariant Riemann tensor transforms with a factor of omega, but G inverse transforms with factor of omega inverse, and therefore the transformation property of Ricci tensor should not carry a factor of omega, and that's what we will find here. Okay, that R tilde is R. Okay, plus of course other pieces, but the expression that you would get is like this. Okay, other pieces that you will get also would have a property that omega inverse something omega. That is what will happen in the Ricci tensor, but not in the Riemann tensor. In Riemann tensor, you have just derivatives of omega and no omega inverse. Okay, so entire expression that you would get is, in the case of covariant Riemann tensor, would be linear in omega, whereas for the Ricci tensor, it is effectively kind of not scaling with omega. Okay, there is a omega factor, but then there is a omega inverse factor also. So to put it a little differently, if you had done the rescaling of from g alpha beta to omega x times g alpha beta, okay, you can do one small global rescaling also with it. So let me kind of write down that expression, not write down, but show you that expression so that, okay, so this is the expression. So instead of doing this transformation, suppose you do this entire transformation times lambda, okay, where lambda is just a number, okay, just a global factor. Okay, then the the Riemann tensor transformation would have a lambda here and a lambda here. This entire expression would also have a lambda sitting around. Okay, whereas the Ricci tensor transformation wouldn't have lambda anywhere, because there is no, there won't be a lambda here and there won't be a lambda here either. Okay, and that you can easily check by just replacing omega by lambda omega. So omega inverse will be replaced by lambda inverse omega inverse, and since lambda is constant, passes through the derivatives and just cancels. Okay, now let's go back to the definition of tensors. The Ricci scalar is defined by contraction of the indices of Ricci tensor, but remember Ricci tensor has, as far as the scale factors are concerned, does not scale. Okay, but Ricci scalar does, because G inverse scales as omega inverse. Okay, so therefore Ricci scalar transformation property should be R tilde goes as omega inverse R plus a quantity which goes as omega to the minus 2 times some derivative of omega, which is precisely what we get. Okay, so that is what we should get when we do this computation. Okay, so it is a useful thing to remember this kind of mnemonic, because every time you try to do these computations, uh, you need to at least get a quick picture as to how many g's and how many g inverses are there in your expression, and this way of remembering that Ricci tensor is effectively G inverse derivative G, whereas Ricci scalar is G to the minus 2 times derivatives of G. Okay, is a useful mnemonic to remember. Okay, any questions about this? Okay, if not, then let's proceed. So what we'll do is, whatever are these exercises telling us, which are not very complicated exercises, but just have to kind of carefully pull out pieces. There are no cancellations or anything, just rearrange terms and order them correctly. Okay. But once you do that, once you know each of these pieces transformation properties, then you can collect all this and put it in the transformation property of the wild tensor. Okay. So if you do that, then you get an expression like this. I'm just writing down everything. Okay. So the first part is how the Riemann tensor transforms. So maybe okay. So wild tensor is defined this way. So first piece is what how the Riemann tensor transform, which is this one. The next piece is the one where how the Ricci tensor transforms. Okay. Now just a few just about a minute ago I told you that Ricci tensor does not transform with any omega with it. Okay. But we have written omega here, but that omega is coming from these metric pieces, because if you write down G tilde R tilde, R tilde gives you R again. Okay, that is the transformation property that we looked at. Okay, but G tilde will give you omega times G. So this omega factor comes from these G's and not from any of these R's. Okay. Similarly, the transformation of Ricci tensor has some quote unquote inhomogeneous piece. That inhomogeneous piece was omega inverse times derivatives of omega. But that omega inverse piece will again go away simply because G would contribute to omega, and that's why it is only derivatives of omega but no omega inverse. Okay, fine. So similarly, there is a term. I'm sorry, I forgot to write the which is scalar here. Oh no, it's here. Okay. Uh, so similarly, there would be a term involving a term of this kind. Okay, and a piece involving the Ricci tensor, Ricci scalar. Okay. If you write down all these terms and put them together, you would find that this entire expression is just omega times C alpha beta gamma delta. Okay. In other words, all the terms that you would get here, okay. So there's a two derivatives acting on omega coming from Riemann tensor, and two derivatives acting on omega comes um, from the Ricci tensor. Sorry, there is this bracket missing. Okay, but each one of them has a bracket actually of its own. This thing. Uh, these terms, if you check them carefully, they would cancel out. Then there are these terms which are kind of local Laplacian acting on omega. Those terms will cancel with this piece. Okay, and effectively you should land up with an expression in which all these derivatives acting on omega kind of getting totally weeded out, and whatever remains is the Riemann tensor here, and a metric times Ricci tensor here, and metric square times Ricci scalar here with a factor of omega. Okay, so that is the property. But as I said, that this object is actually conformally invariant is what we wanted to show. But what we actually wanted to show was that the wild tensor with one contravariant index is conformally invariant. But what we have shown is that the wild tensor with all covariant indices in fact scales as omega. Okay. So all we need to do is to define a wild tensor with one contravariant index by contracting it with the metric inverse. Okay. Now metric inverse, of course, transforms under local rescaling as omega inverse, which kind of takes care of this omega, and therefore we recover the result that C tilde alpha beta gamma delta is same as C alpha beta gamma delta. So if you do a local rescaling uh, of the metric, then the wild tensor is invariant under that. Okay. Fine. So this is something which is useful if one is trying to study, say, conformal properties of the space time. Okay, and in that case, it's a wild tensor which would remain invariant under the conformal transformations. And if you kind of look at how wild tensor behave, it will give you results which are independent of the scale. Okay, so scale invariant properties are the kind of properties that you are trying to look at. Then wild tensor is the right object to look at. Okay, any questions? Okay. Okay, so let's change the topic. We'll talk about parallel transport now. So in the Euclidean space, we have, of course, a notion of parallel lines or a notion of parallel vectors. Okay, and that is defined in a very simple way. Suppose we have two vectors in the Euclidean space, and if we call them parallel, then that's defined by writing the components of the vector like this: A as ax I plus ayj plus azk, and similarly b as b in terms of bx, by, and bz. And the statement that two vectors are parallel in the Euclidean space, excuse me, two vectors are parallel in Euclidean space means that the ratios ax by bx is same as ay by by is same as az by bz. Okay, if you have that, then you claim that these two vectors are parallel. That's a kind of usual notion that we use in Euclidean space. Now, of course, this notion does not make sense in curved space simply because two vectors at two different locations cannot even be compared. Okay, they can be compared only if they are defined at the same point. Okay, but in the same at the same point, the parallel vectors is kind of a trivial thing to define because you have defined a single vector space in which you talk about two vectors being parallel. Okay, in Euclidean space, typically you talk about two vectors defined at two different locations and still talk about them being parallel or not. Okay, fine. So we want to ask a question as to how do you define a notion of parallel vectors at two different points in a space uh, which is typically not flat, okay, in curved space, okay. But let's try to kind of start with the flat space, okay. So suppose we have two vectors, let's call them A and B, okay, and they are defined at two different points, okay. Then what we will do is in the flat space, we transport a vector from say vector A from the point at which it is defined to a point at which a vector B is defined, while keeping the vector constant throughout the process of the transportation. Okay. Once you take it to the point where the B vector is defined, then we can check whether the A vector transported in this fashion to a point where the B vector is defined, whether it is parallel or not. Okay. And the point is that, like, once you have done this, if the if the transported vector A is actually proportional to the vector B, then we would say that a vector A is parallel to vector B. Okay, fine. Now this process that is kind of very easy to do in flat space, okay, and is what is called the parallel transport. So parallel transport is the process where you move a vector from along a particular path, keeping it constant all through. Okay, that is how the process of parallel transport is defined. Okay, so now remember one thing, that it is, this statement is clearly defined with respect to a path along which the vector is being transported. Okay, now when you're working in flat space it doesn't really matter. Okay, but as soon as you start talking about the curved space, then it matters as to which path you are actually taking. Okay. Any question? Okay, so let's proceed. Okay, so the natural question, of course, is that is there any sense in which we can define the parallel transport on a curved manifold? We just talked about how we would parallelly transport a vector in a flat space. We want to ask a question: how would we do that in the curved space? Okay. In other words, how do we know whether two vectors defined at two different points in the curved space are parallel or not? Okay, it's an equivalent question. Okay, either you parallel transport a vector from one point to another point, or you give a notion which will tell you how to compare two vectors defined at two different locations and uh, tell whether those two vectors are going to be parallel or not. Okay, fine. So as I said, that unlike the flat space, in the curved space, this statement depends on the path that you take to transport a vector from one point to another point, where one vector is defined at, say, point P, another vector is defined at point Q. You transport a vector from point P to point Q. What is the path you have taken is important in deciding whether the two vectors that you get, uh, whether they are parallel or not. Okay, fine. So let us consider a curve which we write in terms of a parameter lambda, and let's write that curve as x alpha of lambda, and uh, the requirement of constancy of a vector or a tensor along this curve. That is a statement that we made some time ago about parallel transport, that you hold it constant, okay, throughout the process of transporting the vector along a particular path. Okay, so we need to define a notion of constancy of the vector, and the statement of constancy of the vector is that that when you look at a parametric curve, which is of course parameterized by value of the parameter lambda, you have a tensor t. You say that the tensor is held constant if, as you change lambda, the tensor doesn't change. So dt by d lambda is 0. Okay. Now that of course can be converted into derivative with respect to space time of the tensor by writing it in this particular form. Okay. So that is the statement of holding the tensor constant while you transport it along a curve. Okay. Any questions here? Okay. So what we are trying to do is something which can be depicted by a diagram like this, something which I have not drawn. I have just picked it up from the net. I tried, but it was just taking too much time for me to get this diagram right. Uh, so so what we are looking at is something like this: that you suppose you define two vectors. Uh, of course, we are not doing. I mean, the description that I am giving is not the same as the description in this picture, but one can try to interpret it in that fashion if you wish. Okay. But suppose you start with two vectors. One is the red colored one, the other one is purple colored one, and these vectors are tangent to a particular curve, okay, and then you want to transport it along that curve, holding it to be tangent to the curve all along, okay. So you kind of transport it all the way to to what we would have called an equator, okay, and at the equator the vector would be pointing this way. On the other hand, if you look at this purple vector, and that is tangent to another uh, curve, and if you transport it along that curve, okay, you would land up at the equator as a vector like this, okay. Now, for the equatorial curve, both these vectors are actually normal to the curve, okay. So if you transport any one of these vectors, either this or that, uh, to say this one from point B to point C, you will land up with a statement that the vectors are actually parallel, okay, because under the process of parallel transporting along the curve, you end up getting these vectors parallel, although when you started off at point A, they were not parallel, okay. So parallel transport uh, clearly depends on how you transport those vectors, okay, along which path, and how, and after transporting, bringing it to the same point, you can do a comparison and check whether the vectors are parallel, okay. In this particular case, we show that they are parallel, but it's not necessary that for every choice of uh, path and choice of initial vectors, the answer would always give you that they are parallel. Okay, definitely not true. Okay, so coming back to what we are doing, we define the tensor in general to be constant by saying that as you change the parameter lambda, the tensor does not change. Okay, so let's go ahead and ask how we are going to utilize this. Okay, fine. Now, now remember that this expression has the following feature, that while this statement says that the tensor is held fixed under this procedure of following it along a particular curve which is parameterized by lambda, when you write it in this particular form, uh, you this expression is not covariant or not of tensorial form. Although dx alpha by d lambda is a vector quantity, the derivative of a tensor, remember I have not written any indices on this tensor uh, because it can be an arbitrary index tensor, but all we need to remember is that T is a tensor of some rank, okay. Partial derivative of that tensor is not a tensor, okay. So therefore, this equation is effectively not a tensor equation, okay. So, and we know that, like, if you don't have a tensor equation, then you cannot really make invariant statements, because by invariant I mean independent of choice of coordinate system, because in some coordinate system this quantity could vanish, in some other coordinate system it would be non-vanishing, okay. So to avoid that, what we could do is we replace this quantity by defining a covariant derivative along a path, okay, and that is defined in this particular fashion. You define d by d lambda is equal to del x dx alpha by d lambda times covariant derivative instead of partial derivative, okay. So if you use this notion, then the expression is covariant, and therefore we can uh, make a statement in any choice of frame, and it should be true in all other uh, frames which are related to that frame by coordinate transformation. Okay, fine. So now we define the parallel transport of a tensor along a curve parameterized by lambda as covariant derivative of that tensor is equal to 0. And now this statement is independent of choice of frame. Okay. So to put it a little differently, this way of defining the notion is suitable for a local frame in which gamma is 0. Okay. Whereas this is a covariant form of that expression. Okay. Which you could have written down in any coordinate system. And in this particular case, I have explicitly written down the indices. It could have k contravariant indices and L covariant indices. Okay. Then this equation corresponds to a tensor with k contravariant and L plus 1 covariant indices, one of them coming from this covariant derivative. Okay. And we claim that this quantity is equal to 0. Okay. Fine. So as I said, that dx sigma by d lambda is of course a vector, is a tangent vector to the curve parameterized by lambda, and therefore this is already a tensorial quantity, rank 1 tensor. Okay, and this piece is a covariant derivative of a tensor, and therefore is still a tensor. Okay, so therefore this entire equation is a tensor equation. If it is shown to be 0 in one coordinate system, then we are guaranteed that it will be 0 in all other coordinate systems which are related to this coordinate system by coordinate general coordinate transformations. Okay. Any questions here? Okay. If not, we can proceed ahead. Yeah. So as I said that it would hold in all frames which are related to this one by GCT. Okay. So suppose instead of writing down some arbitrary rank tensor, suppose we look at vector quantity. Okay. Suppose we uh, want to do a parallel transport of a vector. Okay. Then this equation can be written as dx sigma by d lambda times covariant derivative of v. Okay. Where v is v can be written in this particular, the covariant derivative can be written in this particular form, where uh, first piece is of course partial derivative and the second piece involves the Riemann crystal connection. Okay. Now, since the tangent vector is typically non-zero, would imply that this expression uh, should be vanishing. Okay. So this is the kind of statement that uh, tells us what happens on the parallel transport to a contravariant vector. Okay. Okay. So, uh, so there are two things that one has to be careful with when one does the parallel transport. One of the things I already talked about, and that is depends upon the path that you choose for doing the parallel transport. Okay, but there is another piece that is important, and that is that it depends on the choice of the connection. Now, remember, I just said that this equation is a tensorial equation, and therefore it doesn't matter uh, what frame in which you can compute this parallel transport. So I should qualify what I mean by the statement that it depends on the choice of connection. Uh, Remember that we have been only looking at the connection which is written in terms of metric and its derivatives. But in general, you can write down more general form of the connections, of which Riemann Christoffel is only one of them. Okay, Riemann Christoffel connection has a property that is metric compatible. By that I mean that if you take a covariant derivative of the metric with the covariant derivative involving Riemann Christoffel connection, then that covariant derivative of the metric vanishes. Okay. On the other hand, you may have a form of the connection which is uh, form the connection which is not having this property in the following sense, that the way we wrote down gamma alpha beta gamma in terms of the metric and its derivative had the property that if alpha was a contravariant index and beta and gamma were covariant indices for the connection, then it was symmetric in beta and gamma. Okay. More general connections that you could write down may have a property where it may not have any specific symmetry property with respect to exchange of beta and gamma. Okay. If you don't have a specific symmetry property, then you can always decompose that connection into a piece which is symmetric under exchange of beta gamma and a piece which is antisymmetric under exchange of beta gamma. Okay, the if the piece which is antisymmetric under exchange of beta gamma vanishes, then we are back to metric compatible connection. But if it is not, then you need to keep track of those that pieces, and typically that term where the the part of connection which is not like Riemann crystal connection, but part of connection which is antisymmetric in the covariant indices, okay, is uh, is called torsion. Okay, and one has to keep track of the torsion element when one tries to study gravity in the presence of non-symmetric uh, connections. Okay, so fine. So coming back to this, uh, parallel transport of course depends on a choice of curve as well as choice of connection. If your connection is always metric compatible, then it tells you that the metric can be parallel transported. Okay, fine, because d of by d lambda of g alpha beta would just be 0. Okay, because that is written in terms of covariant derivative and that vanishes. But if the if the connection inside d sigma is not metric compatible, then this piece may not vanish. Okay, and although it doesn't happen when you try to do theories or ordinary theories of gravity, but it could happen, or it in fact it does generically happen if you study supergravity theories. Okay, so gravity theory may not have it, but supergravity theory generically has uh, torsion elements inside those covariant derivatives. Okay, we will not get into torsion from this point on. Okay, we are doing four-dimensional pure gravity story. Okay, any questions here? Okay, so let's step back a little and look at this equation again. So this statement of constancy of a tensor along the curve is a natural thing to define. Okay, uh, that you say that as you change the parameter lambda, t does not change. Then you use the chain rule to write down the equation in this particular form. Okay, that this equation is not covariant under general coordinate transformation is a separate issue. But that this expression could be written in this particular form would have been a natural expectation by using the chain rule. But what we did was we said that it is not covariant, and therefore we demanded that the equation should be covariant, and we replaced the d by d lambda by capital D by d lambda, where we replace the partial derivative, where we replace the partial derivative by covariant derivative. So the natural question is that how do we know that the capital D by d lambda piece that we are using, okay, where is it? Yeah, so question is how do we know that when we replace this by capital D lambda, it corresponds to parallel transport. Okay, so to do that, we'll have to do a separate computation. Okay, and let's do that computation by looking at two vectors defined in at two neighboring points. Okay, so instead of this picture that I had drawn where we kind of go from north pole to equator kind of stuff, we will not do that kind of computation. We'll do a small uh, transport from x naught to x naught plus delta x naught. Okay, now to do that, what we'll do is that we will choose the coordinate system, a primed coordinate system, in such a way that the Riemann crystal connection in the primed coordinate system vanishes. Okay. So in the primed coordinate system, of course, V alpha would go to V alpha prime, W alpha would go to W alpha prime. Okay, where V and W are defined in unprimed coordinate system to start with. Okay, fine. Now The statement of parallel transport is the following, that we say that two vectors v and w are related by parallel transport, or if they are parallel vectors, if in a particular coordinate system, in this case I have chosen it to be primed coordinate system, v alpha prime is equal to w alpha prime up to a correction which is order delta x naught square. Okay, so that is the correction. There is no linear in delta x correction which relates v with w. Okay, so it's directly quadratic onwards. Okay, now uh, we can write down the vectors in the unprimed coordinate system in terms of vectors defined in the primed coordinate system through their transformation property, which is given here, del x alpha by del x prime alpha prime times v of alpha prime. Okay, but since these vectors are defined locally, okay, this transformation property has to be evaluated at a point at which the vector is defined. Okay, so del x prime by del x prime, del x alpha by del x prime alpha prime is defined globally for a global coordinate change. But what matters to us is only its value defined at a particular point at which the vectors are defined. Okay. Similarly for w, but now it is not defined at x naught prime, but at x naught prime plus delta x naught prime. Okay. So that is the relation between the vectors defined in unprimed coordinate systems to vectors defined in primed coordinate system. Okay. Fine. So let's try to ask a question. What is the difference between the two vectors? Okay. So in the unprimed coordinate system, we just write that as v alpha minus w alpha. Okay. And that can be written in terms of prime coordinate system variables by just using this relation. So v alpha minus w alpha is equal to this expression minus this expression on the right hand side, which is what we'll write. So that is del x alpha by del x prime alpha prime evaluated at x naught prime times v alpha prime minus the same quantity evaluated at x naught prime plus delta x naught prime, because that is the place where w alpha was defined. Okay, times w alpha prime. Okay. Now, of course, in the prime frame, to leading order, these fellows are same. Why? Because we said that the change is going to happen at quadratic order. So to leading order, they would be same. Okay. So therefore, we could replace one of the variables by say w alpha prime by v alpha prime when you do a leading order computation. Okay. Fine. Now, when you are looking at this expression, del x alpha by del x prime alpha prime computed at x naught prime plus delta x naught prime, okay, and try to compare that expression with del x alpha by del x prime alpha prime evaluated at x naught prime, okay. If you want to do that, then you actually need to do a Taylor expansion of this expression, uh, and at order by order, you have to set delta x naught prime to be equal to 0. Okay, which is essentially means that you do a Taylor expansion and evaluate that at x naught prime. Okay, so that's what I have done here. You write down del x alpha by del x prime alpha prime defined at x naught plus delta x naught prime plus delta x naught prime is equal to same quantity defined at x naught prime plus the next term in the Taylor expansion, namely this second derivative of x alpha with respect to x prime alpha prime, sorry, I forgot a prime here, x prime beta prime times delta x prime beta prime. Okay, and so on, and all higher order pieces. Okay, is that fine? Okay, so to first order in delta x prime, what we would find therefore is a quantity which is a second derivative of uh, the coordinate change times delta x prime beta prime times v alpha prime. Okay, and the reason for that is when you plug this back up there, okay, uh, the first term here times w alpha prime is an expression which is del x alpha pi del x prime alpha prime evaluated at x naught prime times v alpha prime minus w alpha prime. So that term vanishes to leading order. Okay. So therefore, if you set that to 0, the first non-zero term is the second derivative of x alpha with respect to prime coordinates times delta x prime beta prime times w. Okay. But w, of course, to leading order can be replaced by v, and that is why I have written down this expression as v. Okay. Fine. Okay. So therefore, we get this expression. We can massage this expression to bring it to a better form. But maybe I can stop here and we can start the next lecture. We could pick up the thread from here. Okay. We need to use some properties of Riemann Tensor connection to replace various terms here. Okay. Any questions?
So,
Yeah.
what would torsion generally do to, like, let's say, geodesics?
Well, they can affect geodesics, definitely. I mean, it would be part of, so instead of writing the Riemann Christoffel connection, you could write down torsionful connection, then it would affect the uh, geodesic. It is there in the
Yeah,
equation.
but like, uh,
The deviation would be
like
different.
if I'm using a connection with torsion,
Yeah.
like what different would it be from
So that's what I'm saying.
these
That
like
without
non-tensor?
torsion versus with torsion, the geodesic would be different. Even infinitesimally, you could see a
In
deviation.
what sense? Okay.
I mean, there is one extra term. You have to just
Is it
solve the
like
differential equation. No?
I mean like physically would it like be related to some kind of rotation or
No, no,
something?
no. It's like, let me give an analogous situation that will kind of explain what will happen. Suppose you are considering a particle in gravitational field. Okay, then
Yeah.
if the motion of the particle, I mean, if it is if it is freely falling in that gravitational field, then it will follow the geodesic. Okay, fine.
Yeah.
Now, imagine that that particle is not just a particle with mass, but it also has a charge. Okay, and besides having only the gravitational field in the background, you also have some electromagnetic field, say electric field. Okay, you don't have to have too much complicated stuff. Then what happens is that your geodesic equation is not just the equation that we have written down involving Riemann Christoffel connection, but it also involves the gauge field. Okay.
Hmm.
Now, because of that, the solution to this equation changes simply because non-trivial gauge field affects the electric charge, and that force plus the gravitational effect put together is the actual geodesic. Okay. What happens in the presence of torsion is something like that only. Okay. The torsion is,
Okay.
you can think of torsion as some kind of an antisymmetric field generating a new kind of force. Okay. And because of the new kind of force, the particle, if that particle experiences that force, it won't follow the usual geodesic, but follow a little deviated geodesic because the additional force is acting on it. Okay. Is that fine?
Uh,
So
okay.
there are of
Yeah.
course a lot of
So
yeah, please.
is
Please.
that not directly like in some way can we relate torsion to some particular kind of torsion as we have done for connection? Like we said, connection has a property that like covariant derivative of the metric is zero.
Yes.
So can we define torsion in a similar way?
By
Not the covariant derivative should be zero, but something else.
yes, yeah. So you can show that if there is a torsionful connection, then if you take the covariant derivative of the metric, then that is not zero, but it is related to torsion tensor. Okay. it is equal to torsion tensor. Okay.
Okay.
So and I mean, as I said that, like, if you are studying theories which are beyond ordinary gravity theories, like as I kind of said, say for example supergravity theory, then you do have torsion, and in that case you need to actually